Okay, so it's my pleasure to introduce you to Matthias of Facebook as a guest speaker. We will talk about haptic mixed reality, exploring applications in surgical simulation. He did his diploma, I guess, master diploma design, Braunschweig, Heuristic. He's now
Okay, thank you very much for the introduction and also for the presentation. Good morning, everybody. It's a pleasure to have this opportunity to talk about some of our research. This is the first seminar talk I'm giving that is broadcast live, so I hope there's also somebody looking at me remotely. Yeah, I would like to talk a little bit about what we're doing in haptic mixed reality. As already mentioned, I'm in Innsbruck in computer science. I'm chair of computer graphics. The group is relatively new, so I can just briefly say something about the group. It's called the Interactive Graphics and Simulation Group. We are only 3 years old now. Work on physically based simulation, so simulation of deformations, of fluids, of cutting processes. Computer haptics, so things that are related to the sense of touch, and virtual augmented reality. So, especially augmented reality methods is interactive. And the talk today will cover actually some of these areas. Yeah, we're 10 people right now. We still have some positions to fill, postdoc PhD positions, so if you miss somebody, let me know. Anyhow, this is what I want to talk about today. I first want to give you the idea of haptic mixed reality. So, a little bit more of the concept behind it, and then show you 2 applications where we try to apply this idea, especially in the context of medical applications. One is for palpation and more recent work on surgical drilling. To set the stage a little bit, so we developed surgical simulators for a long time, more than 15 years. We have developed several systems. These are just 2 examples. On the left here, this is an older one for hysteroscopy. That's the endoscopic inspection of the uterus. I'm not going to talk too much about the simulators themselves. What I want to focus on is the haptics, the sense of touch in these systems. Still, anyhow, I will just run a video here. So this is how such a simulation looks like. This is all computer generated. So we have real-time computation of flow, of deformations, detecting collisions, cutting tissue, and so on. The second system here is arthroscopy. That's just a different area of the human body, as in the knee joint, for instance, where of course we also simulate. The difference is that this one over here, you see this in the next slide, haptic device, while this one over here only has a plastic knee. So all the touch feedback comes from the plastic object itself. Also a short movie here. Again, this is a simulation. This is what you see on the screen. Both interventions are minimally invasive, so we have small openings through which you insert your surgical tools and then carry out the intervention. Now, what I wanted to get at is the haptics, so the touch feedback. When you want to interact with such a simulator, you also want to get a sense of touch when you're colliding with objects. This one here uses active haptics. That means this green cloth, there's a haptic device hidden. I've seen such a device before that generates forces to the user based on patients, so that he has a feeling of touching something. The other version is already mentioned. Here we just have a plastic model that replicates the anatomy, but this is not active, this is just a feedback model. In the community, people call it passive haptics, but of course there's no real device, actually it's just a passive prop. Both have advantages and disadvantages. Active haptics is relatively flexible because we can program the feedback. Unfortunately, these devices are quite costly. Most expensive ones can go up to hundreds of thousands. We have to do expensive computations. The update rates, generally people say this should be 1 kilohertz, so we have to update the compute forces 1,000 times per second. There are other issues here, like stability issues, device compliance, etc. Of course, the feedback in a sense is more stable. It's of course from a real object. We don't do any computations, but it's only one model. So we have a one-to-one mapping from the virtual environment to the real object. So there's no flexibility here. We can't show different cases. That's why we thought about maybe combining the two. So mixing something like real feedback over here with computed feedback over here. So because it's augmentation, augmented reality, so augmented passive haptics with active feedback. So do something like this, but create some additional touch stimuli. So we want to mix together real and virtual, and this is of course a known concept. So if we take a step back here, maybe you've heard about this Milgram's Reality-Virtuality Continuum. To describe this idea that you can have mixed realities, where you have real components and virtual components and mix them together. Here just illustrated with some images from a robot arm. So here is the real robot arm on one end, and here is the fully virtual scene simulated. On the other end, in between, we have combinations of the two. Mixed reality, this could be augmented reality, where we have the real environment and overlay some simulated virtual information. And over here, this augmented virtuality, this continuum, maybe only the simulation, but there are some props that interact. This concept is only limited to the visual augmentation, so to add something in the images. And our idea here is to extend this also to the sense of touch. So you can think of it that your touch feedback, so when you interact with something, could come from a real object, or it could come from a virtual object. But of course, the interaction forces have to be displayed somehow, but there's no actual real solar cam forces in this case. And well, this is what people already looked at, but maybe we can combine the two. So have something like a haptic mixed reality where real objects, a part of the touch feedback is computed and mixed together as real feedback. And thinking of this as two dimensions, so once is haptic mixed reality and this visual mixed reality, together with colleagues, there was this idea that you can maybe think of a Visuo-Haptic Reality-Virtuality continuum extending this idea of Milgram, that on one axis we have the touch sense, and on the other axis we have the vision sense. And according to this, you can also classify different systems. So depending on if it's only real feedback in a sense, to touch on real objects, so you have full virtual computed haptic feedback, or a mix of that will be in different regions of this graph here. Let me also mention here my collaborators, Sophie John, he was a postdoc in my group at ETH, and Samuel Chair from Heuristic. We worked on several of these ideas together. Now here, this column, this is the haptic mixed reality, where the idea is to mix together touch feedback from the real environment and from the virtual. And I want to give you a few examples here. Actually, one where everything we see is only real, so we don't actually view the images, and another example where we also mix the haptic feedback together, but here we have fully virtual things. Before I come to that, this haptic mixed reality, so this is also what we call augmented reality or augmented haptics. Let me give you a short explanation of the general concept. So we want to modify forces. So let's say we interact with something deformable. We get from this interaction from the real object the normal contact force. Imagine pressing on something. But instead of experiencing this one, we actually want to experience a different target force. Modifying this somehow. That means that with an additional haptic device, attached to a probe here with which we interact, this device we render an additional force. and these two together give me this different experience of the force. The best would be to try this out yourself. So you play around with the haptic device, I can only show it to you. But at least I have some movies here which maybe explain this a little bit more. So here you see a user poking the sponge that is fixed to a table with the same, with a certain amount of force, and you see the resultant deformation. This is without this augmentation. And now with this augmentation, with the same force, maybe you can just visually see it, the deformation is smaller. That means that it feels stiffer to the person interacting with this object. You try to push against the user so that it feels like rubber, for instance, instead of a sponge. So conceptually, I'll give you another example again, first without augmentation, and then the same object with augmentation, and it also feels like an object with a device made of different material. So just the concept here, very simple case, it's like a spring, so if you press in 1D, that's the 1D case, an object, you apply a certain force, for Newton's law, so also reaction force, which is proportional to the displacement, just assume Newton's law, and just say that the force is proportional to this displacement. Now, if we add a haptic device in here that also presses, so let's say it presses also in the same direction as the user, that means that the user force gets smaller if we want to get the same deformation. So the device is now also pressing, it's kind of assisting the user. That means that the object, this reaction force of the object is now equal to the sum of the two. The user has a different force now, the tilde F, which is smaller. So to the user, this object now feels softer in a sense, because the device assists in the motion, in the compression. And this idea we can now use to mimic different materials. So if you want to say, you want to show a certain stiffness, it's called K, you have to generate with the device an appropriate offset force so that the user feels as if he's interacting with an object that has a stiffness of tilde K instead of the actual stiffness K. So we mix together these forces, we add offset forces to the direction. This is the whole idea of the haptic augmentation. We have a model, we have some target material stiffness that we want to generate in this case, and this is sent to the device so that the user has the impression of interacting with a different material. There are a lot of other things to consider here. I don't want to go too much into detail. For instance, you have to know when to start rendering the forces. So you have to know when the contact happens. This can be done with a force sensor. So as soon as you touch the object, you know, okay, we are in contact now. Now we can start displaying forces. Other things as like filtering, PD controllers, or here this was just any elasticity for real objects. You have to characterize this first. You have to compensate gravity inertia of the probe and so on. But I don't want to cover this right now. But this idea we have used in different contexts. For instance, to change the weight of objects. So we have to lift up an object and move it around and make it heavier or lighter. Then to change the feeling of surfaces, so that if you move over a surface, that something appears to be of different material. So for instance, in this case, a glass surface we could make feel like being a rubber surface, or in the other case, a rubber surface feels like a glass surface, smooth. Or also squeezing stiffness, that if you lift an object and squeeze it, that we again use these additional forces that it feels softer. Different. Interaction here is a little bit like with two chopsticks, more or less. So think of lifting a piece of sushi. Okay, so this is the general idea of this haptic augmentation. And now I want to give you two examples where we try to apply this in the context of a radical interaction. The first one is for palpation. So palpation means that you interact with tissue and try to find underneath the tissue material that is stiffer, has a different elasticity. For instance, for breast tumor screening, it's typically that you try to find small nodules which could turn into a tumor. And we wanted to look into the idea if we can develop an algorithm that does this augmentation in such a context. So the setup, very simple. So the prototype work. If you have a silicon hemisphere, interact with that gives us the real feedback. We now want to create something virtual underneath the surface that is not really there, but we measure the appropriate forces that it feels like a tumor underneath the surface that we can position arbitrarily, give different sizes and different material properties, which you then can palpate for. To mean again, we have forces from the real object. The target force that we should feel is were a real tumor, and then the force that the device has to exert on the user or add to this real force, so that mixed together it feels like underneath the surface is something. It's not easier. And we have haptic augmentation, haptic mixed reality. To do that, we need a model for these forces here of the tumor. These forces that we get from the real object, of course. These forces have to be rendered by the device, so we need some kind of algorithm to use these forces. And this has to be done during real time when the user interacts. Someone have to know it. And of course, we have to mix into this. And here we developed a very heuristic model that I want to explain. Basically, this dynamic model that captures the tumor response, and this is calibrated or generated based on pre-processing. We first do measurements of real objects, once with such a inclusion in there, once without, and then from the difference we try to actually generate this force response, the model for this force response. The underlying contact dynamics model is a Han-Crossley model. That is a standard model for contact dynamics, where the force magnitude is just computed based on the positions and also velocities here. To tune this, we just have to tune 3 parameters: the stiffness coefficient, the damping coefficient, and this exponent here. So we need measurements, positions, velocities, and forces, and from that we can actually tune these parameters. The velocities typically get just from the positions via some differencing. So, so we do some parameter identification, so meaning we take some measurements from a real object, measure forces, measure positions. This follows Hadali that are so recursive least square optimization identifier. This takes about 10 to 20 seconds. So basically, you probe the object several times, get the data, and then you tune this model. Of course, there's a velocity in there, so we also have a viscoelastic gain. This is done twice, so we do this once for a model, as I said, without such an inclusion, and not with an inclusion, so really existing inclusion, and from the difference, we try to get this force model for this tumor component that the device has to render. So the first step is this: we start poking such a silicon hemisphere without anything inside. The forces, positions, and velocity estimates, and we use this Han-Crossley application to get this Han-Crossley model H1 that characterizes the force feedback from this hemisphere without anything inside. No tumor sample. To give you an idea of how this works, here are just some example materials: different stiffness, sponge, foam ball, rubber, armrest, and the measured data and some estimated curves, so you get an idea of how this approximates this feedback. So this is displacement for and the forces with regard to displacements. And also you see the viscosity here, the releases. The second step then is to get the model for the case where we actually have this tumor inside. This is our physical tumor. So we manufacture these samples with smooth on silicone. So we have a shape, and we first generate this stiffness sphere and then put it inside, and then put the same material around it to generate these samples. Here we have to, here we can more or less arbitrarily poke. Here we are limited to a position directly on top of this tumor. And again, get forces, positions, and velocities. Now we assume that here these forces now are a mix of the tumor contribution and the whole homogeneous object. That's why we subtract here from these forces that we measure the previously identified forces from the previously identified unfortunately model. Kind of, so we hope here to only keep the forces that characterize the tumor. So we get these new forces Ft, where we kind of remove or hope to remove the component of the surrounding material. And this, these new forces and the positions and the velocities we now identify again with the 100% identification process, this model that hopefully describes contribution only of this tumor. And this we will then use for our heuristic haptic rendering to compute the forces due to the now, how does this look like? This heuristic rendering model. Again, the contact detection happens via force sensor. So as soon as we press on something, we can see there's some contact force. So we start rendering. We don't necessarily have to know the actual geometry here. We just have to know that we have contact and where. But the measurements that we did before here in this step are only here from a point that's closest on the surface to the tumor. That means these force curves are only correct for this case. The question is now, how can we generate forces at an arbitrary position? So when we're somewhere else on the surface here and start pressing down, again, we want to get a contribution from the tumor, but somehow exactly here where we measured, we somehow have to now approximate these forces based on the information that we have. We developed a rather heuristic model for that, which I will explain in the next slide. This is a lot of formulas that I will step by step develop how we did this. I have to say this is heuristic, but we will see later on the performance plots that it doesn't work so bad actually. So what we have so far is, this is the tumor position, this is the contact point on the surface, S, where we initially started measuring, and L0, this is just the vector between the two. This we already know from the start. And we also have this uncrossly model for the displacement forces. Now, if we would contact here now and press just along L towards the tumor, then we could just use this to remove the forces. It means the force that we would experience is just the normal direction of the surface, and the magnitude, so this is just a unit vector, it's given by so when we press on here. The problem is when we contact over here and start pressing down, also again to this deformed silicone, we now have to use this to also generate similarly these forces, but we have to scale it somehow. So it's a bit heuristic. We assume that this is all homogeneous. We assume this to be just a point, it's a sphere, of course, but it's an arbitrary shape. We also assume it's relatively homogeneous everywhere. Contribution just drops off this distance here. So we try to approximate it. What we now have here is this contact point on the surface. Later, during the arbitrary use interaction, we compress this. So this is where the tooltip is of the device. And probe. The force, we then say, okay, This is just the contribution of the tumor. We just say, okay, we render it from the center of the tumor towards my current interaction point. This is a force vector, this is a direction. And still, what we still have to determine is the magnitude of the force. So this f here, this function, that tells us how this is just a normal vector in this direction. We have to know this function f here, how large this vector is. This we want to somehow get from this cross model. Of course, we can't just now take x and the velocity anymore, because we're not directly going down here towards the tumor. We have to scale this. It's a bit heuristic, but I'll explain this. So if we look at a vector connecting these 2 points to get a reasonable estimate for this x here, we just project our vector here, p, onto this vector, and take the length of that one that we then want to plug in our Haptic model. So this x here is just the length of this projection. This is the unit vector t, and p is projected onto that. So this gives us the length of that projection. Now this we can use directly yet. So there's a tilde, because this length, of course, would stay the same if I just push somewhere over here and project it. We also have to consider somehow how far away we are from the tumor, and for that, just look at the distance from the initial measurement point. And this is just a weighting factor where we take the length of L0 and divide it by this length, t, which kind of gives us a smoothing out. So the further away we go, kind of weight here that reduces this x. And this now, this weighted x, plug into our Heuristic model, and this gives us the force magnitude of the force vector that we exert on this tumor component. It is very heuristic, but for this very simple geometries, simple material, it works reasonably well. So here you see some comparisons. You see the displacements in a couple of plots and the forces, where the forces compared and measured in the computed forces. We have 2 cases. One's a little bit softer real tumor and a stiffer real tumor. And this is the 2 rows. And we measure its 3 positions, just the normal direction for now. One's directly on top of the tumor where we get the initial measurements. Then just a centimeter to the side, position P, and another centimeter to 8 side for C. And then what we do is we either measure the forces from the real object, or we measure forces and add to that the computed forces from the tumor, and then compare the curves. So the red curves here are from the augmentation, the line augmentation, and the stippled black curves are from the real measurements. And well, qualitatively, we are not so far off with our model here. So the augmentation, the largest error, I haven't quantified it here, but is in this case B, because here we are still close to the tumor, so there's contribution of the tumor, but due to a heuristic model, it's not so exact. And if we go further to C, then this error gets smaller because also the tumor component is blended out to the weight. But the overall shape is doesn't look so bad actually. The nice thing is that with this model we can do it fast, so we don't have to solve for finite element simulation, for instance, in real time. And we wanted to okay. Again, a video, because you can't touch it yourself, but this, can we say that the blue field, this spherical object underneath this silicon hemisphere. This is just a rendering where we have visualized the way that it's semi-transparent underneath the surface, the position of the tumor, and actually we also shifted according to the interaction a little bit. Of course, you can feel what the person is feeling here now, but you only have to believe me that you can actually touch also this virtual tumor underneath the surface. We did some experiments to see how well this worked. So we did a user study where we asked the users for two things. We asked them to give similarity ratings, and we also measured detection times. So users had to poke two samples. They had to find a tumor in there. These tumors were either real or augmented, virtually generated. We measured first the time it took them to find these tumors, and then they also were asked to rate the similarity between these two cases. This was from 0 to 100, where 100 means they're more or less the same, and 0 is completely different. At the start, there was of course a calibration session. We had 4 conditions. Once we had 2 times the same real tumor inside, that's the same stiffness. Then once with 2 real inclusions, but once a real and a hard one, once a soft one. And then we compared the virtual to the real. They both were stiffer, and then virtual to real, they both were soft. And we wanted to see, do people actually notice differences here? Is it clear that something is augmented? In fact, we didn't tell them that it's augmented. We just told them there's something inside of these hemispheres, and please find it. This was also not visible to them, so this was hidden underneath this box here. The only feedback they had was these contours of these hemispheres, so that it was easier to position the device on top and start pressing.
Yes, and why didn't you compare virtual hard versus virtual soft?
Because of course, we could have done more cases here, then the experiment takes longer. We wanted to basically see if these should represent the same, if people notice that it's virtual instead of the real one. But yeah, we didn't do the other ones. Of course, we could also do that. Virtual hard against virtual soft. Well, then you would have a baseline to compare maybe with this case. But in this experiment, we didn't have it. Yeah, we had 12 participants that carried out this task. Here are some of the results. So on the left, the similarity scores for the 4 cases. This case here is where both times we have a real harder tumor, and here the similarity rating goes up to 180, not even 100. The real harder versus the real softer is clearly different, so this drops down to 35, more or less. While here, these are the cases where we compare the real to the augmented case, so the real to the virtual. And it drops down from the 80, but it's not that they're clearly different. For example, the result. One way ANOVA shows that these are considered the same groups. This is the time for finding these tumors. So this is only per case we have. So here we have 4 times the real hard case, 2 times the real soft, and then only once in the virtual cases. Interesting enough, again here, the time mainly depends on if the tumor is hard or soft, and not on if it's real or virtual. So they also took similar times to find these tumors. If it's harder, it goes faster. If these tumors are softer, it's inside the system. So again, using this virtual augmentation didn't change this too much. In fact, so this was the first example. Of course, there are still a lot of problems. So we did a lot of simplifications. We only assumed homogeneous material. The shapes are very simple. There's hemispheres and spheres. The rendering is very heuristic. It works only well for normal compression, for shearing. The aim is actually become much larger, so if you start compressing and shearing, I have some work on the paper, but there it doesn't work so well anymore. Also, the interaction is not really palpation. You would usually use this with your fingers, not with probes. But for that, we would use these sensors on the fingertips and also actuators on the fingertips. Sensors may become available at ETH. We did some work, and a group in Basel is now continuing this. We have very tiny 6 degree of freedom force sensors. that may be possible. For the actuation, we still have to see how to do this kind of thing. But at least the underlying algorithm of augmentation seems to work reasonably. Okay, so this was So this was one example for applying this haptic augmentation, haptic instrument, and medical setting for the patient. The other example I wanted to give is more recent work, that is for surgical drilling. So this is just preliminary work. We just published this year on that. Here, this is for this example simulator I've shown before, where we have a plastic knee. And one intervention can be that you have to drill into the bone. Of course, you don't want to drill into the real bone or into this plastic bone here, because then you have to replace it after training. So again, you want to simulate this somehow. That you have the impression that you're actually drilling into something, but you're not really drilling. So again, we want to use haptic augmentation here for this drilling. Somehow have to give the displacement into the bone. You have to render stiffness for different bone material. So in the corticalis, you have very dense bone. In the spondylosa, you have softer bone. And also there are some vibratactile feedback, so some vibrations. So with this also we have to generate some. I want to focus here on generating these stiffnesses, which we want to do with haptic augmentation. The idea is that we take an actual surgical instrument, so a surgical drill, put all the actuation inside of the drill. So when you're drilling with it, you have the feeling that or the impression that you are drilling, also nothing is really happening. Since it has to be inside, it has to be lightweight and small, and also cheap. So the first actuation that we looked into here is the twisted string actuation. This is a relatively new concept. The idea is that with this electromotor here, and as a tip, with just circular strings, so also fixed somewhere else, and then you start twisting. So twisting of the strings, and by that you start pulling this. As it gets shorter due to the twisting. This generates forces, and this is the idea here that we have forces on this part. There's a spring here, so we start compressing this, you feel the spring, and this is forces that we generate with the augmentation here, or with the actuation. Then again, can we use this augmentation from the spring forces. Show this on another slide. First short videos. This is the actuation when it moves. So here, twist and untwist, and accordingly this parts. So here also we want to use augmentation. That means if we look down here, this is the whole setup. We have twisted string actuator here, and the physical spring. And if you push on this side, of course you feel the spring. But then when you start actuating this, you also generate forces, pulling forces in this case. It means you can again augment the forces that you get from the spring. You have the spring forces, normal forces, and then you can pull here to make this feel softer, actually. So the apparent stiffness that we have is just the forces from the spring minus the forces from the twisted string actuator divided by the distance, just again, it's a linear elastic model. And if you now again want to render a specific stiffness, then we have to exert a certain force with our twisted string actuator that the user feels that it's a different stiffness. It's softer than the actual spring, the actual stiffness of this spring. So we have to generate forces with the twisted string actuator. There are various models to compute this. A similar one from Pali et al. Is just based on the angle, so the accumulated twisting angle here. So when you twist the strings, parameters for that are the stiffness of the whole string assembly, which you can determine before the initial length x0, and it's not contracted yet. And RT, this is the radius of this string assembly, which changes over time. For that, that's also closed form to actually compute that. So we can control the forces just by changing the zeta, this angle here of the twisting. To give you an idea how the forces look like, so depending on this twisting angle, we twist this a couple of times, this is the forces that we generate. See here 2 points, that first it's nonlinear forces that we generate. Another important point is that this is the untwisted state, or maybe if we do some retwisting, maybe we start here. To generate high forces, we actually have to twist several times. You will see this later in the plots. This is actually a problem, because if we want to generate high forces at the start, it takes a while to twist up the string. This is a disadvantage of this actuation, actually. So here just some results of this. So first plot shows how we can use this actuation to give the user the feeling of interacting with material of different apparent stiffness. So we use augmentation, gives the person the feeling that he interacts with material that has these different stiffnesses. This is just measured from a force sensor and then displacement versus the forces. The bottom lines, this is the augmented forces, which are relatively nicely linear here. The yellow one, this is the real feedback you get without the augmentation. You just press without the twisted string. What you can see here is that we can generate nicely this different target apparent stiffnesses interacting with something that if you press it. Now we also want to see what happens if we change between these stiffnesses. So this next plot plots over time the different stiffness. We want to simulate a stiffness jump after a distance of 3 mm. So just like you're drilling into something. After 3 mm, the stiffness changes. The first plot here is from something soft to something hard. This is the target here. And here we have from something stiff or hard to something soft after 3 mm. So this is the time it takes to 3 mm. And here you see 2 problems. Maybe the first one is here, this overshoot. Since we have a low stiffness here at the start, that means we have to create a high offset force with our twisted string actuator. And when we go here to the higher stiffness, that means we have to pull less, so it has to untwist. This untwisting overshoots a little bit and retwist again. This is why we have this overshoot. But the bigger problem is at the start, because as I said, when we have a high offset force here, so it feels softer, the twisted string has to twist up. And for high forces, it has to do this actually a couple of rotations. That's why it takes a while. This is the disadvantage of the system. Final measurement here, where we also included now damping into the model, so not only linear elasticity, but some energy dissipation depending on the velocity. So again, there's a stiffness jump here from higher stiffness after 3 mm to lower stiffness. So this is the different slopes that we have here. But now we also have different feed rates, so different velocities. It was controlled with an external robot from 1 mm per second to 6 mm. We now extend our model with some damping. This is just to model, for instance, friction between the drill and the bone material. And you can see here nicely again, depending on the different velocities, we have these offsets in the forces because there's energy dissipation. Again, at the start, it doesn't work too well, but after some distance, we have a relatively reasonable behavior. So we took this and then put it into a prototype. So this is just a drawing of this inside of this mock-up drill. It's not a twisted string actuator. There's also a linear potentiometer to get the distance of the compression. This is kind of the drill tip that we put on the surface somewhere and we start pressing, and then with this augmentation you feel like you're drilling into different materials. There's also some vibration actuator in here that I didn't talk about. comparison, this is a 3D printed tool, and this is just the real surgical drill that you use in orthopedics. And the short video. So here, this is now the user uses this in drilling into, or virtually drilling into a surface. Of course, this all moves inside. This is mock-up drill. And what you will see is that first the user presses more or less with the same force. First, there's a small movement because there's corticalis, so there's a dense bone. And after a certain distance, so he will go into the spondylosa and then he moves a little bit faster because the stiffness is low. But he applies the same forces. So it's like drilling through the long bone. First dense material and then less dense material. So this is first the hard part and then the soft part, and then drill. So the softer material again first feels stiffer, then you press and use it. The idea is to use this together. Then this is the whole virtual simulation that I've shown before of the knee. We had some interventions. We then take a drill, put it inside of the knee, the drill into the bone, and then do some additional interventions. Okay. Also, here's some discussion. Actuation was our first choice, but actually we ran into several problems here. One is that maximum displacement is limited by the spring length, so when you compress the spring fully, you can go further. With the twisted string actuation, you can only pull so far, so you twist it up and this pulls the whole thing, but you can't push it, so you can make the spring, can generate a higher stiffness, so the whole overall stiffness range is limited by the stiffness of the real spring and the contact harm. This problem that I mentioned was the time delay at the start when you want to generate large pulling forces because you have to twist quite fast with these large forces, which is also a disadvantage. And also, since we have the string materials, the examples we used cotton yarn fiber, we shifted to some stronger materials that are used in fishing lines, for instance. The problem is that we continuously twist this up, exert forces on it, so this actually we have to start thinking about lifetimes, because this can become damaged and then actually fracture. So there are quite a lot of problems here. That's why we currently look into an alternative, just with a ball screw mechanism, maybe with a screw, and then something that's linear and moving on it, and we start rotating, which avoids several of these problems. One thing is that in the simulator we have a tracker that uses magnetic fields. That means we have to avoid anything that distorts these fields. That's why we looked initially at these strings that we can place the motor a little bit outside of the field. We have to see if we find the right hardware for this to avoid disturbing the field too much. Okay, so that's what I wanted to talk about. Just to sum up, I hope I could explain this idea of haptic mixed reality, where we do haptic augmentation similar to what is done in visual augmented reality, only known as forces, mixing real with virtual. I mentioned this extension of the idea of Milgram's Reality-Virtuality, Continuum, now it's touch and vision. And I showed two examples. One, at least the concept of for haptic augmentation, that we can mix forces in there that we feel like they're virtual tumors in the tissue samples. And the final example for surgical drilling, where we vary the stiffness of bone while we're drilling or apparently drilling into something. This is a mock-up surgical drill. Okay, just to acknowledge also the collaborators. Currently, Juan is working on this in my group as on his PhD in this work. Yeah, we also work in other areas. Of course, I don't have time to talk about that. I will just run some movies here at the end. This is more visual augmentation that is combined. Only use haptics, so on this 3x3 plot, it would be somewhere here on the left. So I'll just let this run. And with that, I thank you for your attention. And of course, I'd like to answer questions if you have any.
Questions?
I have a question. Did you do also a user study for the last example?
For the haptic drill?
Yes.
We were not there yet, so we tried ourselves, and it is actually quite convincing. So you can put it on the surface, and you feel like, okay, you're drilling to something harder than something softer, but we haven't done a formal study yet. And what we also have, what I should mention here, is that it is for something minimally invasive. So there will be a pivoting point. So we have this knee, and this drill goes through a pivoting point. So it's a little more fixed than what you've seen in the movie here. But yeah, we have to do some experiment on that. So, which will work.
More questions?
Yeah. At the beginning of your talk, you had this video of this coloscopy, right?
Well, the one was hysteroscopy on the left, and the other one was arthroscopy.
Okay.
For me. Yeah.
Okay. But the question stays the same. So how could a haptic device work in these cases? Because you have this very standardized device that people use, the camera device, and then
okay.
so like how could you apply the
left
forces in such a setup?
Yeah. So both interventions are minimally invasive. That means that we have small incisions, where the tools, we have long tools where they are inserted. So we always have a pivoting point.
Yes.
Now there are some devices that are specifically designed for that. So there's, for instance, a commercial device from a company called Actuation that provides exactly the 4 degrees of freedom that you need to force feedback. So you have 3 rotations, so 1, 2, and 3, and 1 translation. And this, the device directly gives you. You just have to insert the surgical tool. Yeah. And then depending on how you interact, of course, you compute the collisions with soft tissue, you compute forces based on that, and these forces then you exert with the device. That's, for instance, one solution. The other solution is that this is my surgical device, and this is the pivoting point, that you fix the device at the tip with a phantom, for instance. So you just provide the force feedback as a tip here.
Yes.
That means you can do 2 rotations, 1 translation, but usually this rotation you don't have any feedback. But there, the feedback also is usually relatively small. But this could be another setup where you have the haptic device attached. You can do it inside, but the problem is that your space is limited. So for a knee, it doesn't work, but if you have an abdomen, a body, a torso, then you can hide the haptic device inside.
Yeah.
That's, for instance, what we also did. But for the knee, for instance, there's also a simulator that was developed in Spain, and then one by Symbionics, there they have the haptic devices outside. So you have a plastic knee, 2 haptic devices around it, and then these devices attached to the end of the surgical tools. So different ways to include the devices in there.
Okay, and my second question was about this palpation training.
Mm-hmm.
So usually doctors, they touch with their hands,
Yes.
right? And you have this pen interaction, and that could be odd for them.
That's what I said is in the discussion, that this is the problem, that we have these probes, but we need something finger-based. So we need miniature force sensors, which are more or less there. The problem is that they have to be very small and optimally 6 degrees of freedom, not only pressures, which needs some development, but these will be available very soon. The other problem is how to exert the forces. There are some glove-based haptic devices which kind of pull your fingers back, but these are not very good. So we would have to develop something sort of a little bit into this direction, so finger-based feedback that does more than just pressures, which can be done with some finger-mounted actuations that only on the skin give you the feedback. But this is, we don't have a good solution for that. This was basically to show that the algorithms at least do some work.
Okay, thank you.
More questions?
Yeah, I have a good one. So your examples you showed, there you try to simulate the patient basically. So you try to use haptic feedback to simulate patients for training.
Yeah.
Is there also something reverse where you would use haptic feedback on real patients. So for example, if you would have tissue where you know that it's really easily hurt, that doctors that you would use a haptic feedback device to avoid hurting special kinds of tissue.
Hurting, okay.
Or avoiding to touch any, like, I don't know.
I have to think about it. So one thing that we did, is kind of the other direction, is to use this as a probe. Just like for the exam, to find a small tumor, to measure forces, by just like a human user would do, and then locate where some stiffer material is just by acquiring the forces, just like a scanning device that you could use on a real patient. This is, for instance, in the context of telediagnosis, that maybe the doctor isn't there, somebody can operate the probe and get the data. We had a publication of that, and we looked into the measurement. But to avoid potentially sensitive tissue, you somehow would have to feed the data into it. So you have to know where is this tissue, how do you know when you do the interaction.
I mean,
I think there was actually a work by a group in Japan that did something where they added these forces during cutting. So it's, for instance, if you cut tissue and you want to avoid cutting through a vessel. So they added forces to move you away from that. And they showed this, I don't know exactly which sensors, but they cut the egg yolk out of an egg, out of a cooked egg. We always stayed outside of the yellow part of the egg and only went through the white one, and the forces pushed you back so that you don't cut into the yellow part. And I think they used some optics with it, but this was why I don't remember exactly.
It was called like intelligent knife or something like that. There was an optical sensor integrated in the knife.
Yeah, I think that it was optical, so they looked at the reflections probably from different materials and all that, tried to find the interface. And the idea was also to use this later in surgery, but I don't think they continued. I don't think there's a solution yet that really assists you doing cutting.
More questions? My question was when you talked about the twisted string actuator, having no idea about mechanics. Is the obvious solution to this not a pneumatic pump, which would be really fast, not interfering with the
pneumatic has the problem that you need, of course, a compressor somewhere, and you have compliance. So because air is compliant, so pneumatics is more difficult to control to get these nice tiled curves that you want to have. I think pneumatics may not be the best way to go here. I think the ball screw or maybe a voice coil actuators may be a good solution.
But the ball screw would also need some time to build up high forces.
But it's not non-linear as a twisted string. And it again depends on how high these forces have to be. But it's a little bit faster than this twisting of the string. And our first test with it, we just changed to it. Seems that it's a better solution.
Okay, if there's no more question, then thank you very much again. Next talk on December 13th, and the last one in January 16th. And I think the abstracts are on the website. Okay, thank you.